All right. So the product rule, it's very, like I said, procedural. It's also not overly challenging. Quotient rule isn't even very challenging. It's also very procedural. It's just a different procedure, right? This makes it look like it's probably pretty complicated, but and even this doesn't make it seem much better. But when I walk you through it, you see it's really not going to be that bad, right? So what you're looking at is a product of two functions. All right, so we got two pieces that are being multiplied together. Now this you could actually distribute out and find the derivative using the power rule, but I wanted to show you with a straightforward example how you would use the product rule. So this is what we would call the first function. And this is my second. All right. Why is it the first? Because it's the first one I see. I'm looking at two functions. One of them is the first, the other is the second. All right. What I'm going to do is take that first function and multiply it by the derivative of the second function. Then I'm going to add to that the second function multiplied by the derivative of the first function. All right. So I'm taking the first function as is. No change whatsoever. I'm going to multiply that by the derivative of the second function. So I'm going to take that second piece, that x cubed minus 3. I'm going to take the derivative of that. So remember that understood coefficient of 1, power multiplied by coefficient, reduce the power by 1. We're looking at 3x squared. The negative 3 is constant. Constant has a derivative equal to 0. All right. Then I'm going to add to that the second function in its original form multiplied by the derivative of the first function. All right, so 6x to the first power multiplied power by coefficient, reduce the power by 1, becomes 6x to the 0th power, which is the same as saying 6. The 5 is constant, it goes away. This would be your derivative, which we would call h prime of x. All right, didn't say to simplify, so we don't need to simplify. All right, if you wanted to, by all means, but you run the risk of losing credit for something that you didn't need to do to begin with. That'd be pretty aggravating for you. I mean, for everyone, but for you, because you'd be the one losing. You'd be the one losing points. I wouldn't want that for you. All right. Second example, I'm just going to accentuate the product here and rewrite that radical as an x to the 1/2. We have our two pieces, and by pieces I mean factors. Factors of a product. This is my first function, this is my second function. Again, same structure. Nothing changes. That's what I mean by it's procedural, because you're going to follow the same steps every time and you'll arrive at an answer, and that answer will be dictated based solely on the nature of the function and how challenging it is, for example, to recognize the derivative of, in this case, an x to the 1/2 versus a sine of x. Right? And so the first function gets duplicated as is, no change whatsoever, x to the 1/2. We multiply that by the derivative of the second function. The second function is a sine function. We learned a little while ago that the sine function has a derivative equal to cosine. Plus, duplicate the original second function as is, no change whatsoever, sine of x. Multiply that by the derivative of the first function. So x to the 1/2, remember that understood coefficient of 1, power multiplied by coefficient, reduce the power by 1, 1/2 x to the negative 1/2. And that would be my g prime of x. All right. So definitely a little bit more elaborate than something like, just a simple power rule, but also even like the sum and difference rules. Right. But very procedural. Follow the steps and you get to the end of the line here. All right. So the next one, we have a sine and a cosine. First function, second function. So we write the first function as is, or rewrite it as is. Sine of x. We multiply by the derivative of the second function. Derivative of cosine, we learned a little while ago, derivative of cosine is equal to negative sine. Plus the second function, which is cosine, multiplied by the derivative of my first function. The derivative of the first function, the sine function we learned a little while ago, is cosine. So the notation here was a y, so I would say dy dx. All right. Now, this one actually can simplify pretty nicely, but again, didn't say to simplify, so we're not going to simplify. All right. There will be plenty of instances where you will have to simplify just to be able to even attempt the problem. Let's not force it to happen when it doesn't need to happen. The skill here is learning the algorithm of first times the derivative of the second plus second times the derivative of the first. All right. So that's the product rule. The quotient rule, it's that and a little bit more. All right. So you could see that the formula looks nastier, the words look nastier, everything just looks nastier. Right. But procedurally, it's only a couple of extra steps, and it's not really much more than that. Right. Instead of thinking about two factors that are multiplied, we're thinking about two expressions that are in ratio form. Right. So one's a numerator and the other's a denominator. Right. What we call the numerator, we call that the high term, right? Or you could call it numerator if you want, but you got this little rhyme here, low d high minus high d low over denominator squared, and away we go. I actually never heard of this when I was a student. I didn't hear it until I was like a decade into my teaching career. And it was one of those things where a student explained it to me. They're like, "Oh, you should use the rhyme." And then they shared the rhyme with me. I was like, yeah, that's cool. I'm gonna do it my way. And on the way home, I was like, yeah, that's not bad. Maybe I'll use that from now on. So the next time I taught the course, I was like, I came up with this rhyme to help you remember how to do this quotient rule, and here it is. Yeah, and so no, it wasn't that bad, but it's not too far off. So we call this the high term, if you want to use the rhyme anyway. And we call this the low term. Why? Because it's physically higher, not in value, but like position wise, it's elevated. All right. So what we do is we take our low term and multiply it by the derivative with respect to x of the high term or high expression minus the high term or expression multiplied by the derivative with respect to x of the low term. And then we put it over the low term squared. And you're like, oh, how on earth is that going to help me remember anything? Well, it's not so much that you're remembering this formula, it's you're remembering the rhyme. Low d high minus high d low over denominator squared, and away we go. It's the away we go that sells it, you know? So, because otherwise it's not a rhyme. You need the away we go, otherwise not, you haven't really accomplished it. All right, so what we do is we take the low term, and I'll use my highlighter a little bit more here. I get my low term, which is 2x minus 7. Leave that just as it is. We multiply that by the derivative of the high term or the high expression. Right? It turns out we're only taking the derivative or the result of the derivative is only a single term expression, but that's not really the point. All right, so x squared becomes 2x to the first, or just 2x. The constant goes away, so just 2x. Minus the high, so x squared plus 2. Multiplied by the derivative of low, 2x minus 7. So the 2x is really 2x to the first. That differentiates down to just a 2. The negative 7 goes away. And then we write this over the denominator squared. So 2x minus 7 squared. And away we go. So f prime of x equals all that. All right. And again, not asking you to simplify, although in this case, simplifying wouldn't be too terrible because it's really just basic distributive property. But that doesn't mean you want to do it, you know? So that, I mean, that really is the quotient. There's really nothing more to it than that. Just like with the product rule, we do another example, you see it's really essentially the same thing. You got your high, you got your low. You're just inserting derivatives appropriately. So the low is x, unchanged. The high, well, I want the derivative of the high. So derivative of sine is cosine. Minus the high, which is sine of x. D, whatever the low is. The low is x, the derivative of x is equal to 1. Over the denominator squared, and away we go. So t prime of x would be equal to that. All right, you may be tempted to try to simplify first before getting down to business. In some cases, that's beneficial. In other cases, it's not really so much. Like, for example, in the next one, you might be, like I said, tempted to try to simplify, but I don't see how that's going to be a useful first step, because even if you could simplify it, it's most likely going to involve long division. Unless you somehow guess right with the factors. I mean, it is possible in such a way that it cancels out, then you could be good, but I wouldn't even bother. If you want to go and try to simplify, what I would recommend is putting in the expression to Desmos before attempting to simplify. Okay. And see what comes up. If it's not a recognizable function, then odds are it's probably not something that's going to be a clean simplification. You know, like we're looking at a difference of a power of 1 between top and bottom. So if this were going to simplify in such a way that something nice would cancel out, then it would probably end up being a linear function or some sort of simple rational function. It's neither of those. It's this. This doesn't look like a simplified form of anything. Right? So I would just dive right in and go right down to business here. Right? So since each component is in the appropriate power form, we're in good shape anyway. So low, d high, so derivative of the top, 3x squared plus 3, minus high, so the original numerator as is, no change whatsoever, d low, derivative of x squared minus 1 is just a 2x, over that denominator squared, and away we go, dy dx. All right, it's algorithmic. It's very procedural. That's there's really nothing more to it than that. All right, but number 7, you look at number 7. Actually, number 8 is probably a better example, but I'll do number 7 because you might look at this one and say, I don't want to use the quotient rule. I hate the quotient rule. maybe you hate me because I taught the quotient rule, and you're transferring the hate from one thing onto another. But sometimes you can get around using a complicated rule if you do a little bit of algebra along the way. So in this case, you might consider splitting the fraction. If you have sums and differences sums or differences, in the numerator of a fraction and just a single termed expression in the denominator, you can split it up. I mean, there's other circumstances where you can split up a fraction, but that's the most basic one, right? And so this would become just a clean x plus, keep the base, subtract the exponents, 3x to the negative first plus 2x to the negative second. So once you do that, you got your understood coefficient and exponent of 1 and 1, dy dx, it's just 3 separate power rules rather than one quotient rule. Now, some people may look at that and say, well, I don't like that trade-off. I'd rather do one quotient rule than 3 separate power rules, plus the algebra. I mean, we don't want to neglect that. But I mean, that's a choice. At least you have it, So 1x to the 0, so just a 1, minus 3x to the negative second, minus 4x to the negative third, with no expectation that you bring it back into any other kind of form. All right. In the next unit, we'll start dealing with instances where we do something with these equations, but for now, we're just learning the skills. So there's no need to go too crazy with it. So I'm going to put a star on each one of these. Well, each one of the remaining ones. It seems like they get more and more challenging, but there's always something algebraic that you can do to make your life a little bit easier along the way. All right, so just kind of keep that in mind, or at least something worth considering. All right, and so the last thing that we're going to do is and this will be very quick. Just looking at it doesn't make it seem like it'll be very quick, but I just wanted to show you where the derivative of the other types of trig functions come from. So if we're looking at a tangent function, we know the derivative of sine is cosine, derivative of cosine is negative sine. But I can write y as sine x over cosine of x. And when I do that, I can apply the quotient rule. All right, so again, the low d high minus high d low over denominator squared, and away we go. All right, that rhyme really, I mean, you may not like it yet, but unless you have a really, really good memory for these sorts of things, you're probably going to be looking for a mnemonic device to help you remember this sort of stuff. So if this isn't it, then your journey is beginning and you'll be looking for something. But my guess is that based on personal experience, that it's been pretty good in the past. Low d high minus high d low over denominator squared, and away we go. Just repeat that to yourself about 5 or 6 times and you'll have it down. All right. So my low, I'll get my highlighter here, is cosine of x. D high, so the derivative of my high term, derivative of sine is cosine, minus the high term, which is sine, as is, no change whatsoever. D low, the derivative of my denominator, derivative of cosine is negative sine, over the denominator squared, and away we go. All right. Now, in this one instance, we do want to simplify a little bit, just so we could get a nice, concise rule for the tangent function's derivative. All right. So cosine times cosine is cosine squared. negative sine times negative sine is positive sine squared. And then cosine of x parentheses squared is the same as saying cosine squared of x. All right. Cosine squared plus sine squared, that's the Pythagorean identity. All the way back to algebra 2 or college algebra, that's equal to 1. So we're looking at 1 over cosine squared x, which is the same as saying reciprocal of cosine is secant, so secant squared x. So what we get from this is when we have the function y equals tangent of x, the derivative of that dy dx would be equal to secant squared of x. All right. So that's a little bit of the origin story behind it. But now it's a fact. So you look at it and say, okay, add it to the list of things to memorize. The derivative of tangent is secant squared. All right. Along the same lines, since we know secant is equivalent to 1 over cosine, we could use the quotient rule again to determine the derivative of the secant function. All right. So it all kind of comes together, you know, putting all these concepts together to derive even more relationships that we could then call facts. So now that they're facts, we can use them to derive even more relationships and go from there. All right, so I'll get my cosine squared in at the bottom real quick. Low D high, this is a fun one. Fun in a fun way, not fun in the I'm gonna torture you as a teacher of math kind of way, right? So low D high, so low cosine of x. D high, well, derivative of 1 is 0. Constant has a derivative equal to 0. Minus high, D low, derivative of cosine is negative sine. Cosine times 0, well, anything times 0 is 0. So this whole numerator boils down to just a sine of x. So this is actually one variation of the derivative of the secant function. Right? It's not the classic textbook variation, but it's an acceptable variation. It's actually, in a lot of ways, more useful, right? But we could also write it in a slightly different way. We can break it up so that it's 1 over cosine times sine over cosine. 1 over cosine is the same as saying secant of x. Sine over cosine is the same as saying tangent of x. All right, so we could say dy dx is equal to really any of these. All right, but the one that you'll find in a textbook is this one. All right. So the other two problems are very similar. I mean, cotangent is the same as cosine over sine. So if you wanted to try that one on your own, you could. Same idea with cosecant 1 over sine. All right, so you'd follow the same type of process, but I can tell you, it's kind of a nice little relationship. Cofunctions have derivatives that are negative cofunctions. All right, it's a nice little nifty rule, provided you know what the hell a cofunction is. All right, a cofunction is actually a lot easier than it might sound. You have trig functions that have a co, and you have trig functions that don't have a co. All right, sine and cosine, those are cofunctions. Tangent and cotangent, cofunctions, secant and cosecant cofunctions. All right. So if you know the derivative of a function, all you have to do is find that derivative's cofunction and negate it, and you're good, and you'll have it. All right. So, for example, sine and cosine are cofunctions. The derivative of sine is cosine. The cofunction to cosine is sine. I would just slap on a negative, and that would be it. I'd have my derivative. All right. So you either attach a co or remove a co depending on what you're starting with. So hopefully this will help a little bit more. We're starting with, in the case of tangent, we're starting with a secant square. So cotangent will have a derivative that involves a cosecant square. But since they are negative cofunctions, I'm going to tack on a negative sign right in front. If it was already negative, I would remove a negative sign. All right, it saves me from having to memorize a new rule or reinvent the wheel. All right, secant tangent, that's the derivative of secant. Secant and cosecant are cofunctions. So if I take secant and use its cofunction, which is cosecant, take tangent and its cofunction, which is cotangent, slap a negative onto the front of it, I'll have the derivative of cosecant of x. All right. So that's the value of a rule like cofunction, you know, that's the one at the top there. All right. But again, it could just be sheer memorization. Some people are good at that. I'm not. You know, like if you give me a list of things to memorize, I'm going to look for like nifty mnemonic devices and things along those lines. I'm not going to be able to look at it and say, all right, repeat this to myself 17 times. Got it. You know, like word for word definitions or anything like that. It's just not going to happen. But little tricks like this help me. So hopefully among the 26 people in the class right now, hopefully somebody found value in that. All right. So that's that. Let me stop the recording.